In 1965, one of the real pioneers of computer science confidently predicted that machines would be capable of doing any work a human could do by 1985.
Which we obviously missed.
Yeah, we missed that deadline by about 4 decades. Welcome to the deep dive.
Thanks for having me.
If you've been following the tech space, even casually right now, you know that artificial intelligence is just, it's dominating the conversation everywhere.
It really is. It's inescapable.
Right. But despite all the massive influx of capital and, media attention, there's this massive disconnect between what the public thinks AI is doing and what is actually happening beneath the surface.
Oh, absolutely. The gap is huge.
So our mission today is to just cut through that noise. We've gathered a stack of sources. We're talking deep tech blogs, financial journals, the history of computer science, to just pull apart the actual mechanics for you.
Because we have to strip away the magic, right?
Exactly. We're looking for the mechanisms, how this technology actually learns, why it fails, and how you, as the listener, can practically apply it to your own workflows without getting caught up in the sci-fi panic.
It's an incredibly important distinction to make right now, I think, because the public conversation often just gets derailed by treating these systems as if they possess some kind of underlying biological thought process.
Right, like it's a living thing.
Exactly. And if we really want to understand the trajectory of this tech and how you can actually leverage it, we have to entirely strip away that magic and look strictly at the math.
The math, not the mind.
Right. The real story isn't about sentient machines waking up. It's about statistics, probabilities, and just massive, massive data sets.
I want to start exactly there, actually, with that math versus magic idea, because the baseline assumption for a lot of people, even folks working in tech-adjacent fields, is that these models are reasoning through problems the way a human brain would.
Which is completely understandable, but wrong.
Right. We assume there's a logical deduction happening. Like, treating AI like a human brain is basically like treating a calculator like an accountant.
That's a great way to put it.
Because the material we're analyzing today draws a really hard line between the sci-fi concept of general AI, which is, a system with broad transhuman cognitive abilities, and the narrow AI that we actually interact with daily.
Yeah, that assumption of logical reasoning is probably the most pervasive illusion in the industry right now.
It really feels like an illusion.
It does. And it stems from the fact that we just naturally anthropomorphize things that can communicate with us.
Yeah.
If it talks to us, we assume it thinks like us.
Right. It's human nature.
But replicating human cognition in software is
Yeah.
a fundamentally flawed framing. I
Yeah.
mean, we don't even possess a complete mappable understanding of our own biological cognition yet.
So how could we code it?
Exactly. What we have built instead are just incredibly sophisticated pattern matching engines. They operate purely on algorithms and mathematical rules. They don't deduce, they calculate.
Okay, but, and I have to push back here a little. If there's no actual reasoning happening, how do we explain the user experience?
The chat interfaces.
Yeah.
Uh,
When you're sitting there asking a chatbot to, I don't know, brainstorm marketing copy with you or rewrite a complex email to your boss, it feels incredibly organic. It feels like there's actual comprehension on the other side of that screen.
It is a stunningly effective illusion. I'll give it that.
Mm-hmm.
And the mechanism behind that illusion is what researchers refer to as the stochastic parrot.
Wait, this is a stochastic terror.
Yeah, it's a vital concept to grasp if you want to understand the limitations of current systems. The chatbots you interact with are powered by large language models, or LLMs,
Okay.
and these are massive neural networks trained on just staggering amounts of text. But the crucial mechanism to understand is that they're essentially just probabilistic text generators.
Meaning they're just guessing.
They map the statistical likelihood of words appearing near each other.
Oh, I see. So they understand the co-occurrence of words rather than the actual definitions of the words themselves?
Precisely. Think of a biological parrot. It can mimic human speech with perfect intonation.
Yeah, but it doesn't know what it's saying.
Exactly. It doesn't know what the words mean. It just knows that certain sounds reliably follow other sounds to get a cracker from its owner.
That is wild.
LLMs do the exact same thing with massive data sets. They are predicting the next most likely token or word fragment in a sequence based on billions of previous examples.
So it really is just the world's most sophisticated autocomplete.
That is exactly what it is.
One of the tech blogs in our stack gives a really grounded example of this that I think clarifies that lack of semantic mapping.
The geography one.
Yeah, the Paris and France example. Imagine an AI model. If it's trained on data where it constantly sees the phrase, Paris is the capital of France, It will confidently output that exact phrase when you prompt it.
Right.
But if it lacks diverse contextual data, that same model will completely struggle to logically deduce the reverse, that France is the country where Paris is the capital.
Because it doesn't actually understand the relationship.
Exactly. A human knows those two things mean the exact same thing because we understand the spatial and geographic relationship. But the model doesn't understand geography. It just knows the statistical probability of the word France following the word Paris.
And when you scale that lack of underlying comprehension up to the enterprise level, I mean, you see why companies run into massive trouble.
Oh, for sure.
Businesses are rushing to plug these parrots into their customer service portals. But without rigorous oversight and guardrails, a probabilistic engine can confidently generate eloquent, structurally perfect sentences that are entirely nonsensical
Right.
or factually incorrect.
Right, what they call hallucinations.
Exactly. We call them hallucinations, but that implies the machine is, like, imagining things.
Like it's dreaming.
Right. But mechanically, it's just executing its probability math flawlessly. The math just happened to point to a sequence of words that isn't true in the real world.
Okay, so if it doesn't actually know what the words mean, how does it consistently guess the right word out of the millions in the English language? There has to be an underlying mechanism weighing those choices so it doesn't just spit out a random word salad.
That brings us under the hood to the actual engines powering those probabilities, and that is machine learning.
Okay.
The language model is just the interface.
Right.
The machine learning is the factory floor where the statistical weights are actually forged.
I want to make sure I'm wrapping my head around the actual mechanics of that factory floor. Based on the documentation we have, there are 3 distinct ways we train these models. Let's start with supervised learning.
Okay?
I imagine this is sort of like sitting with a toddler and a stack of flashcards. Like you hold up a picture and if they say cat, you say yes. If they say dog, you say no until they learn to recognize the pattern.
That is a highly accurate way to visualize it. In supervised learning, you feed the algorithm millions of explicitly labeled examples.
Like this is a fraudulent transaction, this is a legitimate one.
Yes. The mechanism at work here is error correction. The system makes a guess, checks it against the label you provided, and if it's wrong, it mathematically adjusts its internal parameters.
It's dials and knobs.
Exactly. It turns those dials to reduce the error rate for the next guess, and it repeats this millions of times until the mathematical weights consistently produce the correct output.
Okay, then we have unsupervised learning. If supervised learning is using flashcards, is unsupervised learning like handing someone a massive, entirely unlabeled spice rack and telling them to organize it?
That's a great analogy.
Like you don't know the names of the spices, but you can group them by smelling them and looking at their color.
Yes, the technical term for that is clustering. You throw raw, unstructured data at the algorithm without telling it what it's looking at.
So no labels at all.
None. The mathematical mechanism here is calculating the distance between data points. It looks for hidden correlations and groups things together based on shared characteristics that a human might never have the time or the computational bandwidth to notice.
And the final primary bucket is reinforcement learning, which seems to be where the system learns by digital trial and error.
Right.
The system or the agent explores an environment and receives a mathematical reward when it does something right and a penalty when it does something wrong, slowly optimizing its strategy.
And the reason we're spending time on these mechanisms is that this isn't abstract academic theory happening in some lab.
Right. This is everywhere.
This is the exact math governing the services you interact with every single day.
The Netflix recommendation engine is a brilliant real-world application of this. When you log in, Netflix is using machine learning to predict what you're going to watch next.
Oh, yeah.
But the fascinating insight from their engineering documentation is that their algorithm deliberately excludes demographic information. They do not factor in your age, your gender, or your location.
Which, mathematically speaking, is a masterclass in separating signal from noise.
How so?
Well, in data science, you quickly learn that who a user is on a census form matters far less than what they actually do.
Ah, behavior over identity.
Yeah. Exactly. A 60-year-old woman in Tokyo and a 20-year-old man in Chicago might both have an identical, highly specific viewing pattern, like stopping true crime documentaries exactly halfway through and switching to sitcoms.
That's hilarious.
But true. The unsupervised learning clusters those two users together based purely on those behavioral data points, completely ignoring their demographic differences.
That makes total sense. I think about Siri in the same way. We use voice assistants constantly, but Siri is utilizing speech recognition to convert audio waves to text and natural language processing to parse the intent.
Right.
But as the architecture breakdowns point out, your phone physically lacks the processing power to do that heavy statistical lifting.
It just can't handle it locally.
Right. It offloads that massive computation to Apple's servers, which is why it fails when you don't have internet. But even with all that server power, because it's fundamentally just matching data patterns, it completely misses the mark on human subtleties, like sarcasm or dry humor.
Because detecting sarcasm requires semantic understanding and situational awareness.
You have to actually get it.
You do. It requires knowing the gap between what is said and the reality of the situation. A statistical model is just looking for the literal word co-occurrences. It cannot weigh emotional context because emotional context cannot be easily quantified into a data set.
Which brings up a massive question. Here is where it gets really interesting.
Okay.
If these systems are so powerful at finding patterns and all they need is more data to adjust their weights and biases, why do we constantly hear about enterprise AI projects completely failing?
Well, this is the big one.
Like, if a company wants a smarter AI, shouldn't they just point it at a larger data set?
The assumption that more data equals better AI is one of the most costly misunderstandings in the corporate world right now.
Really?
Yes. The reality is that an AI model is hypersensitive to the diet it is fed. If you feed a machine learning algorithm a massive data set that is filled with errors, duplicate entries, or outdated formats, you aren't going to get a smarter system.
You just get a faster idiot.
Exactly. You're just going to generate terrible predictions at a much faster speed. It's the classic computer science rule of garbage in, garbage out, amplified by a billion.
So if you're sitting at your desk right now wondering why your company's expensive new AI integration keeps messing up basic spreadsheets or returning irrelevant internal documents, this is exactly why.
It's almost always the data.
The sources cite a study analyzing corporate AI pilots, and the results are just staggering. 95% of these pilot projects fail to produce a return on investment.
95%. And almost every single postmortem points back to the data infrastructure. Companies tend to view AI as a silver bullet,
Right, like a magic wand.
They purchase a complex off-the-shelf model, plug it into their disorganized legacy databases that haven't been cleaned up in a decade, and expect it to magically organize their business. But the mechanism of machine learning requires pristine inputs.
We see the flip side of this in the financial sector data we reviewed. When a bank actually cleans its data and applies these models correctly, the results are incredible.
Oh, absolutely transformative.
They analyzed artificial neural networks designed to predict business bankruptcies and loan defaults. And when they fed the machine learning model clean data, using the exact same predictors that human analysts use for traditional scoring, like the Altman Z-score, the AI achieved a 13 to 30% higher prediction accuracy.
And that margin of improvement in the financial sector represents millions of dollars in mitigated risk.
Huge money.
Huge. But it introduces a massive operational hurdle. Those highly accurate models utilize deep learning, which involves multi-layer neural networks. And these networks are frequently what data scientists call a black box.
Okay, what does that actually mean mechanically? I hear black box thrown around all the time, but why can't the engineers who built the system just look at the code and see how it made a decision?
Well, imagine millions of tiny mathematical dials.
Okay.
In a multi-layer neural network, the data passes through an input layer, several quote-unquote hidden layers of artificial neurons, and then an output layer. As the system trains, it creates its own intermediate rules to solve the problem.
So it's writing its own logic.
Essentially, yes. It adjusts those millions of dials, the weights and biases, in ways that do not map to human logic. It might find a correlation between two variables that makes zero intuitive sense to a human analyst, but is mathematically predictive.
Wow.
Because the decision is the result of millions of micro-adjustments across these hidden layers, it is physically impossible for a human to trace the exact path the algorithm took to arrive at, deny this loan.
Which moves us from a technical quirk to a massive business liability.
Oh, huge liability.
If you operate in Europe under GDPR or California under CCPA, you are legally required to be able to explain to a consumer exactly how their data was used to make a decision about them.
Right.
So if your own predictive AI is a mathematical black box, you simply cannot comply with those privacy laws.
This is exactly why explainable AI is receiving so much funding right now. We've built statistical engines so complex that we can no longer interpret their internal states. And that's a massive roadblock for deployment in regulated industries.
Okay, so if massive language models have hallucination issues, and deep learning requires pristine data and mostly lives in corporate finance or giant server farms, it really begs the question of accessibility.
For the average person.
Yeah.
Huh.
Is this technology actually useful for an individual trying to learn something new or streamline their own work without running into these massive structural problems?
This is where the landscape is shifting rapidly. The public focus is entirely on the giant, generalized chatbots that try to be everything to everyone.
And consequently hallucinate.
Exactly. But the most powerful, transformative applications of this technology are hyper-focused tools that solve specific problems by restricting the AI's environment.
Our sources highlight an incredible space for this that a lot of people overlook, which is Google Labs. It's an experimental playground where you can see this restricted, hyper-focused approach in action. The most prominent example is Notebook LM.
Which originally started as Project Tailwind.
Right.
Notebook LM is a perfect case study in overcoming the hallucination problem through a mechanism called grounding.
Ground.
Yeah. When you use a general chatbot, it's pulling from its training data across the entire messy internet. With a grounded tool, you upload your own specific sources, a dense medical textbook, your company's HR PDFs, or your own lecture notes.
So you provide the data.
You provide the universe it lives in. The tool restricts the AI's search space entirely to the documents you provided. It is forbidden from pulling outside information, which mathematically neutralizes the probability of it making up a fact.
It turns the model from a creative writer into a strict synthesizer. It can instantly generate mind maps, study guides, or extract key themes strictly from your material. But the feature that completely blew my mind is the audio overviews.
Oh, they are incredible.
You can upload a 40-page technical manual, and the system synthesizes your specific text and generates a highly realistic conversational audio deep dive, much like the one we're having right now,
It's wild.
where two AI voices discuss the material, pull out analogies, and explain it back to you.
Mechanically, it's taking the synthesized summaries and running them through advanced text-to-speech models that have been trained to include conversational fillers, pauses, and pacing. It makes dense data instantly accessible. And that focus on accessibility is a recurring theme in these experimental spaces.
Absolutely. There's another tool in there called Learn Your Way. You feed it a complex text, and you tell it your age and a specific interest.
I love this one.
So if you're a high school student trying to learn complex computer science data structures and you love basketball, the AI will completely re-level the text to explain algorithms using basketball analogies.
It is the mechanism of a one-on-one human tutor, scaled infinitely through machine learning. We also see this in a tool called Learnabout, which shifts the interaction model entirely.
How so?
Instead of the user asking a question and the AI dumping a massive wall of text in response, the AI acts as a conversational guide. It feeds you a concept and then actively checks your comprehension.
Oh, so it quizzes you.
Yeah, it asks you questions to ensure you're keeping up before moving to the next level of complexity.
It shifts it from passive information retrieval, like a search engine, to active engagement.
Exactly. When you restrict the model scope and give it a highly specific interaction framework, the utility just skyrockets. There are also creative tools like Stitch for UI design or Opal for no-code apps.
But looking at these tools that can read a textbook, rewrite it using original analogies, test your comprehension, build mini-apps, and generate conversational audio breakdowns, we have to address the oldest fear in the book.
The job question.
Yeah. What happens to human jobs? If these systems are this capable at synthesizing and presenting information, are we just automating ourselves into obsolescence?
It's the single most common anxiety surrounding the technology. But to truly understand the future of human work, we actually need to look back at that 1965 prediction we started with.
Okay.
Why was he so confident that machines would do all human work by 1985, and why was he so completely wrong?
Because they ran headfirst into something called Moravec's paradox.
Yes.
This is a fascinating piece of computer science history. Early AI researchers discovered something incredibly counterintuitive. High-level intelligent tasks, like proving complex geometry theorems or playing championship-level chess, were remarkably easy to program into early computers.
But the easy things were hard.
Exactly. Unintelligent tasks, things a 2-year-old does effortlessly, like recognizing a face or crossing a cluttered room without tripping, were impossibly difficult for the machines.
And the reason for that paradox comes down to evolution. Billions of years of human evolution have optimized our sensory motor skills and basic perception to be highly efficient. and completely unconscious.
We don't think about walking.
We don't consciously calculate the physics required to catch a ball, right? Our brain just does it. Because we don't know the step-by-step logic of how we do it, we couldn't easily write the code for a machine to do it.
That makes total sense.
Conversely, abstract mathematics and logic are very recent human inventions. They're entirely conscious, rule-based systems, and computers excel at executing explicit rules.
So how does that historical paradox reframe the fear of job loss today?
Well, it reminds us that human cognition and value in the workplace are vastly more complex than executing logical rules or parsing data. The historical precedent, supported by the corporate data we've reviewed, strongly suggests that AI is a tool for augmentation, not outright replacement.
It's not a magic wand to replace your whole team.
No. Just as the spreadsheet didn't replace the accountant, it simply allowed the accountant to do far more complex financial modeling. These statistical models take over the rote data processing.
Freeing us up.
Exactly. This forces human labor to pivot toward the things the machine mathematically cannot do: strategy, empathy, complex physical navigation, and nuanced problem solving. Embracing it actually unlocks productivity.
But we still have to ensure that as these statistical tools become more autonomous, they're pulling in the same direction we are, which brings us to the concept of AI alignment.
Right, AI alignment is the true frontier of computer science right now. Remember, an AI system is strictly defined by the mathematical metric it is programmed to optimize.
It just wants to hit its goal.
The danger isn't the sci-fi trope of a machine developing malice. The danger is a machine ruthlessly optimizing its programmed goal without any contextual understanding of human values.
A great grounded example of this from the sources is social media algorithms. If you program an AI to maximize user engagement metrics, it quickly learns that outrage and polarizing content keep people clicking longer than nuanced discussion.
It's the most efficient path to the goal.
Right. The AI isn't malicious, it's just executing its math perfectly to achieve the goal you set. But because that goal wasn't aligned with the broader human value of, a healthy society, the output is actively harmful, even while technically being a success on the spreadsheet.
That is the alignment problem in a nutshell. It is the challenge of translating complex, often contradictory human values into mathematical weights and biases that a machine learning model can actually process.
Which sounds incredibly difficult.
It is. Pointing these extraordinarily powerful engines in the exact right direction so they don't cause harm is the most critical work happening in the field today.
We've covered a massive amount of ground today, moving from the history of computer science to the realities of corporate data. To pull all of these threads together for you listening, the systems dominating our feeds right now are not conscious entities, nor are they flawless plug-and-play solutions for messy businesses.
Not at all.
At their core, they're highly sophisticated probabilistic engines. They require pristine, clean data to function correctly. They excel at pattern recognition far beyond human capacity. And when deployed in restricted, hyper-focused environments like Google Labs, they are actively evolving into personalized tools that can really augment how you learn and work.
We have spent this entire deep dive breaking down the mechanics of how machines learn to interpret our data. But as these stochastic pairs become increasingly fluent and their ability to mimic human empathy and logic becomes mathematically indistinguishable from the real thing, I think the most interesting question isn't whether the machine is truly thinking.
What is it then?
The question is whether you, sitting on the other side of the screen, will eventually stop caring about the difference.